Welcome everybody. This is our Chapter 9 notes on atmospheric processes in severe weather. And I think that people oftentimes think of weather when we talk about natural disasters and natural hazards, and certainly there's going to be a lot of examples of those in this unit right here. But as we always do, we start out each unit with some kind of a case study, and we're going to touch on this. I'll refer to it more during the class, in the in-class lecture, and then we'll actually revisit it at the end of the chapter as well. But the city of Moore, Oklahoma, is a little bit south of Oklahoma City. And in 1999 and in 2013, it was struck by two tornadoes that were virtually identical in their path, where they hit, and also in their power, and the power being virtually off the charts. So we had our 1999 tornado, which killed 36 people. All right, we were upwards of 300 miles per hour in wind speed. That is just a monstrous tornado, and 10,000 homes being destroyed as well. And then a very comparable one in 2013. We're going to look at the path in class, and we'll see how the wind speeds and the track were very similar, although the number of people killed was reduced, and I think it's a result of learning some lessons from 1999. But Moore, Oklahoma is kind of a good case study. So here is Moore right here, and you can see there's virtually nothing left. I mean, even the trees, I mean, there's no leaves, not even any small twigs in the trees. That's about all that's left right there. And so this tornado that came through in 1999 was, like I said, absolutely monstrous. But in order to understand tornadoes and other storms like that, we need to really understand about the concept of energy. And so that's where we're going to start our notes right here. Energy. All interactions in the atmosphere deal with the transfer of energy. So to understand energy and force and work and power and all that stuff, we have to kind of start with just the fundamental understandings of physics. And one of the basic measurements in physics is the concept of force. Force is, like for example, your weight is a force. All right, weight. I'm going to do a different color right here. Black isn't too good. Let's go with red. All right, your weight. Your weight is a force. Now your body has a mass. All right, so you've got a mass, but that mass is being accelerated by gravity. Gravity is what pulls you down to Earth, and so this right here, force equals mass times acceleration, is one of the fundamental equations in physics. We call that Newton's second law. And for that very reason, we label the unit of force as newtons. What is a newton? Well, a newton in the metric system, so that's metric, would be the same thing as a pound. We'll call that LB. Don't ask me why. In the English system, okay? Now, it's not the same thing, but a newton is about, 1 newton is roughly a quarter of a pound. All right, they're both measurements of force. They just have different units. So I guess technically you could walk into McDonald's and ask for a Newton burger, because don't they have quarter-pound burgers? Anyway, asking for a Newton burger, they'll probably look at you like they have no idea what's going on, but it's a measurement of force, okay, very much like a pound is. Moving on to other measurements of work and energy, we've got work, all right? And what work equals a force, there, and we have our equation for force up here. Force is a mass experiencing some acceleration. Work is a force applied over some distance, all right? Energy or a force is expended over a certain distance. So, for example, let's say you are standing here. Let's see, here's the ground, and you've got a set of dumbbells. So that's you right there. You're about to lift up. Okay, you do work in taking those dumbbells from the floor and lifting them up over your heads. All right, you've applied a force over a distance, so you've applied work. Interestingly enough, as you're holding these dumbbells over your head, you're not moving them anymore. You've lifted them up, and now you're just holding them there. Even though you feel tired, it's tiring, you're not actually doing any more work once you've done moving them. So work is really a force applied over a distance. What else? Okay, power. Power is another measure of energy, or the rate at which energy is expended. All right? Power equals work over time. That is, how fast do you do work? If you lift a set of dumbbells in a minute, okay, from the floor to over your head, versus if you lift a set of dumbbells from the floor to over your head in 5 seconds, well, you've expended more power doing it faster. So it's the rate, or you might say the time, dealing with time at which work is done. Okay, so power is related to work by time. Work is related to force over distance, and so they're all related right there. So we measure, oh, by the way, we measure power in watts. You probably know that light bulbs are measured in watts. Okay, it's the rate at which they expend energy to give you light. That's metric. In the English system, so that's metric right there. In the English system, you probably know that we measure power in horsepower. All right, now that's about I think it's like 740 watts. It really has nothing to do with horses at all, but those are similar units, just different systems. Okay, and energy itself, which is really what work is. Work is the expenditure of energy. Energy is measured in something called joules. Oh, I'm sorry, that was on the previous page. Yeah, so energy is in joules with a J right there. Work and energy are all in joules. But as we measure the amount of energy in the atmosphere, and there's tremendous amounts of energy in the atmosphere, we measure that in things called exajoules. Like, for example, you wouldn't measure the distance from here to Philadelphia in centimeters, right, or probably even meters. You'd probably measure in kilometers. You'd put a prefix on the front right there. Well, exa means something to the 18th power. Kilo, like kilometers, equals something to the third power, right? The thousands. Exa equals something times 10 to the 18th power. So something with 18 zeros after it. It's a tremendous amount of energy. But we're talking about our atmosphere, and so that's appropriate. By the way, other prefixes you might be familiar with are mega, right? That's 10 to the 6th. That means million. Giga, we're all familiar with that. 10 to the 9th. That's billion. And tera, if you have a terabyte of information, that's 10 to the 12th. That's the billions. And I forget what's between tera and exa, but it's something else. I want to say peta, P-E-T-A. That's right. 10 to the 15th, and then we have exa over here. So all these are prefixes for multiples of 10, something. So we measure atmospheric processes in exajoules. It's a lot of energy being expended. All right, so what kinds of energy can we measure in the atmosphere? Well, you may remember this from maybe physical science in middle school, but we have potential energy. For example, we've got student Bob sitting right here, and over his head is a bowling ball. Okay? It looks like another face, doesn't it? Anyway, it's a bowling ball right there with little 3 finger holes in it. Okay? Actually, Bob should probably not be smiling because there is some potential energy stored in that bowling ball over his head, right? You know what? And the bell just rang. Yeah, sorry about that. I had to pause it there for a second. The bell rang, or the announcement thing rang. Anyway, this bowling ball right here has potential energy. Now, somebody had to get it above his head right there, but it has energy that is stored because what does it have the potential to do? It has the potential to fall down and clunk student Bob in the head right here. All right, so that's why he I mean, he knows it has potential energy, and he's like, uh-oh, something's going to happen. Once it starts moving, however, it's a different kind of energy. All right, so we've got him right here. And once it starts moving down, so say somebody's holding it over his head and all of a sudden releases it now, okay? Once it's moving, it's got now kinetic energy. And kinetic energy is the energy of motion. Most of you are drivers, all right? And when you're taking driver safety courses, you were probably told that cars in motion have lots of energy, and energy that can do good things like move you from point A to point B, and do some bad things like bend up somebody else's fender or wrap itself around a telephone pole. So kinetic energy is the energy of motion. This is the types of energy that are stored in various places in the atmosphere. There's also a type of energy called heat energy. All right, and heat energy is the energy of molecules that are vibrating back and forth. Anything that has any kind of temperature at all, unless it's at absolute zero, has some heat energy. You, the desk you're sitting on, the pencil you're holding, whatever it is, all those molecules have some sort of motion. They're vibrating back and forth very, very rapidly. All right, so all these molecules right here, and they're all kind of jittering back and forth, and we can measure that as temperature, right? And in fact, we call that sensible heat. Now, I don't mean sensible in the term, in the sense of, you've got like common sense, but sensible in that you can sense it. That is, we can measure it with a thermometer. And so a thermometer can measure the energy of any object if you place it in contact with that thermometer. There's another type of heat we're going to be talking about called latent heat, and there will be probably a separate video for this where I kind of describe latent heat, but latent means hidden. Hidden. Sorry, my writing's not that great right here. Hidden, or kind of in the background. And there's a certain kind of heat that is exchanged when something changes phase. For example, when a block of ice, let's see, I'll change to blue right here. All right. We got an ice cube, and it melts into water right there. All right, and water can also be transferred into water vapor. All those little things right there. All right. Every time it changes phase, a certain amount of energy is released. So you could have 0 degree ice and 0 degree water, or 100 degree water and 100 degree the water vapor. But each of these different phases has different amounts of energy in it because energy is given off. We call that latent heat, or latent energy is given off or sucked in depending on what phase that is in right there. And so when we have water condensing from gas to liquid, or from liquid into ice, or vice versa, doing all these different phase changes, a good amount of energy is exchanged, and that energy drives atmospheric processes that we're going to be talking about. This right here is kind of a little example of latent heat. For example, you probably have heard the term calorie before, all right? 1 calorie is the amount of heat required to rise 1 gram of water vapor by 1 degree Celsius. Now, 1 degree Celsius is about 2 degrees Fahrenheit, but you get the idea, okay? So if we have 1 gram of water vapor, and by the way, a gram of water vapor is about the size of a pea, maybe, or a blueberry, okay? It's about 1 gram of water vapor. To raise that 1 degree Celsius, we need to put 1 calorie of heat energy into it. So a calorie is what we measure heat in. It has, I won't say it has nothing to do with food calories. They're related, but we're going to ignore that for the time being. Okay, so if I got solid water down here, every time I put a calorie in, it raises the temperature. All right, so this is really ice right here, right? I'm going to change this to dark blue. Ice, water, and this is vapor up here, all right? If I have a gram of water, I put a calorie in, it raises it a degree. Another calorie in, it raises a degree. But when I bring that to 0 degrees, you would think, okay, if I just add 1 more calorie, it'll become 1 degree liquid water. But that's not true. You have to put a certain amount of energy in just to get it to go from 0 degree ice to 0 degree water. and we call that latent heat. And so that's a solid liquid phase change right here. Same thing is true of going from water liquid, now this is liquid right now, water liquid to gas. You would think that if you raise you keep adding calories to a gram of water, it would raise the temperature, and it does. And we call this sensible heat right here. But once it becomes 100-degree water, you would think, okay, just add one more calorie of heat and it becomes 101-degree water vapor. Not true. You have to put in another chunk of heat just to change the phase over from 100-degree water to 100-degree water vapor. Then once it changes phase, you add more calories, and then the water vapor increases temperature. So this right here, this water vapor, actually has more energy in it than the 100-degree water vapor has more energy in it than the 100-degree liquid water, because you've added all this extra energy right there. And we do call that latent heat as well. So that's a quick kind of crash course in latent heat and heat transfer. Actually, we're going to keep heat transfer a little bit right here. We're going to look at a couple different ways in class that heat is transferred. For example, conduction. All right, conduction is through contact. All right, let's say there is a metal spoon in a hot bowl of, or a hot pan of, I don't know, soup or something like that. All right, and you've got a metal spoon sticking out. That's in the dish right there. If you hold on to that metal spoon for long enough, the energy that is in the hot soup, there's heat lines right there, okay, the energy is going to travel its way up to the end of the spoon and probably burn your hand because it is in contact. Everything is in contact. We call that conduction. Convection is, you might think, what causes all the soup to get hot. For example, let's say you have your burner, your kind of coil burner down here underneath. Well, it's only heating the bottom of the soup, right? What makes the whole soup get hot? The fact that that liquid or that fluid rises up and circulates around. So really, circulation is kind of another word for convection. Any kind of fluid, it can be liquid or it can be gas. But wherever you have hot stuff moving somewhere else and then transferring its heat around, we call that convection. And lastly, we have radiation. You don't even need to be touching that hot coil. You don't even need to be really even close to it to feel radiation coming from it. And that's what we call electromagnetic waves. Probably one of the most familiar types of radiation you're familiar with is light, visible light. But infrared is a type of radiation that comes in waves, and it can travel right through empty space. It doesn't even need any medium or any contact at all to go through. It can go right through space, and you can feel it. And you know, if you're near a source of heat, or even if you're near another person, you can feel heat coming off that other person or that other object. That's a form of electromagnetic waves that we call infrared. And we'll look at a few other items, a few other kinds of electromagnetic radiation along those veins as well. Well, this right here, I just kind of drew for you. All right, here's our typical pot on the stove right here. So we've got radiation coming straight off the burner. We have conduction, that is through things that are in contact, maybe possibly burning your hand. And convection is through the circulation of a fluid. And for right now, let's see, we're coming up on section 2. So I'm going to end this video, and then we'll have a separate one where you'll be able to pick up a little bit later with section 2. So thanks for watching. I'll see you on the next one.